Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be continuing our talk about how to solve nonlinear equations. In particular, we're going to explore solving rational equations. We'll start by defining what a rational equation is, and then reviewing some techniques that we have previously learned in our algebra courses to hopefully be able to solve these unique equations. Now, the first thing we need to do is define a rational equation. We're going to define a rational equation as an equation that contains at least one rational expression. So we're going to say it is an equation. I abbreviate that EQ. So it's an equation that contains at least one rational expression. Now remember, a rational expression is one where we have a polynomial for the numerator and a polynomial for the denominator. So something like, if I'm thinking of an example, something like x minus 3 over x squared plus 2. There's a rational expression, okay? So a rational equation is an equation that has at least one of these terms involved with it. Now, some properties we need to know. We are dealing with fractions here, okay? That's what rational expressions essentially are. We're dealing with fractions. So what are some properties we know about fractions? Some techniques we've used when working with these things before. Well, something I'm thinking about is our work with clearing fractions. That's something we've done in the past. We've also had things like making common denominators. We also have that property where when we multiply to the bottom, we also have to multiply to the top. So here are some properties of certain techniques we've used when working with fractions. Let's see if we can take these techniques and help us solve a rational equation. Notice here, our rational equation, we have an equation, and we're going to say it's a rational equation because one of these fractions has a polynomial numerator and denominator. Yes, it's very simple, but we can say that this fraction has a monomial denominator of x. So let's start by trying to figure out how can we isolate this x, because that's essentially our goal, right? Let's remind ourselves that the big goal here is to isolate x. Get it by itself. Figure out what that value is. Well, couple ways we can go about doing this. What I'd like you to do is pause the video, try out a technique that you might be thinking of how we can get x by itself on one side, okay? Pause the video, give that a try to write down what steps you're doing, and when we come back, we'll take a look at a couple different methods and see if your method fits with one of ours. Well, hopefully you had some time to work through a certain technique and come up with your solution. One of the first things that we're going to review is the idea of trying to simplify down what we have here. Notice that when we are working with this equation, we have two fractions here and one fraction here. It might be a good idea to simplify things down to where we have just one fraction on each side. So, is there a way that we can combine these two fractions together? Well, notice that we're trying to add them, but they have different denominators. One has a 5 and one has an x. Well, hopefully you're thinking back to our work with rational expressions, and you're thinking, I can add 3/5 and 1x together because we can easily make a common denominator. What would that denominator be? What do we have to get both of these denominators to share? Well, hopefully you remember that if I multiply this fraction by x over x, and if I multiply this fraction by 5 over 5, we would end up with a 3x over 5x plus a 5 over 5x equaling 2/3. What we just did there is we said, well, what does this denominator have that the other one doesn't? It has a 5, so that's why I multiplied this side by 5. This one had an x, so that's why I multiplied that by x. So we're able to come up with a common denominator, and we can add these fractions together. We get 3x plus 5 over 5x equaling 2/3. Okay, how does this help us? Well, one of the things that we could do is we can go and say, let's cross multiply. We could multiply both sides by a 5x and both sides by a 3. So we would end up with 9x plus 15 equaling 10x. That's the idea of cross multiplying here, or really all we did was we just multiplied each side by the denominator of the other. So we can subtract 9x from both sides. We end up with 15 equaling x. There's our answer. X is going to be 15. And we can check our work. Let me change up colors here, and let's try to check what we got as our answer. We had 3/5 plus 1/15. That should be 2/3. Well, if I gotta make a common denominator, I should multiply this fraction by 3 over 3 to get 9 over 15 plus 1 over 15. And when I combine those, I get 10 over 15. Well, 10 over 15 simplifies to, if I divide 5 from the top and bottom, I get 2/3. It works. So this technique that we just utilized, where we go and group together all the fractions on one side, and then we either cross multiply or really just multiply each side. Or you can kind of say we've just multiplied each side by the other denominator. And we essentially have our answer. Let's write down what we did here for method 1. Method 1, I'm going to say, is the get all fractions to combine. So this is that where we get all fractions on one side to combine. Step 1, make common denominators. Once we have common denominators, we can go and say that we can combine the fractions. And when I say combine, I mean add or subtract, do whatever it's telling you to do. We can then cross multiply to get rid of the fractions. And then we can solve like normal. Once it's solved, I'm also going to say that we can check our work to make sure that we have the correct solution. So review what we did here. We went and we made common denominators. Once we had the common denominators, we combined the fractions together. We want to get all the fractions on one side to combine into one thing. When they are one thing, when you have a fraction on one side and one on the other, you can just cross multiply. Easy as that. Once it's cross multiplied, you've gotten rid of the fractions and you can solve it like normal. Hopefully this technique is making sense to you. It's really relying on the work that we've done previously with rational expressions. What I'd like us to do now is see if there are any other techniques that we could use for solving this. I'm going to go back to our previous problem, and I want to clear some space. In the previous problem, we said our overall goal was to isolate x, and we have the same goal here, isolate x again. But this time we're going to do it differently. we're not going to do it by just simply combining fractions together. What I'd like you to do is pause the video and take a minute to see if you can think of any other techniques that we could use for solving an equation that deals with fractions. All right, well, hopefully you had some time to think about this task of trying to solve an equation dealing with fractions where we're not really going to go and combine the fractions together. That was the method we already learned. Is there another way of going and isolating the x? Well, hopefully you're thinking back to work that we've done both in previous courses in algebra as well as at the beginning of the semester, where we actually go and clear the fractions. In the previous method, I said, let's go ahead and combine fractions together. What if now I say, let's get rid of all of the fractions first? So, the idea with clearing fractions is I can multiply both sides of the equation by some value to get rid of all of the denominators. And we said before, choose the value that's the common denominator for everything. Notice my denominators are a 5, an x, and a 3. So what's a common denominator between 5, x, and 3? Well, that would just be 15x. So I'm going to multiply both sides by 15x, the common denominator. I'm going to distribute it through, and I want you to see what happens to the denominators. So let's go ahead and distribute 15x through. So here's what we get when we distribute the 15x through. We're applying it to each term, and when we actually multiply the 2/3 and the 15x together, we get 30x over 3. So I'm going to go ahead and keep multiplying, and before I go and simplify anything, I'm just going to multiply across. So 15x times 3 is 45x over 5, plus we have a 15x over x, and then 30x over 3, I guess I'll just leave that for right now. So we can go ahead and simplify all of these. 45x divided by 5 is 9x. And 15x divided by x, that just cancels out to be 15. And here we have 30x divided by 3 is 10x. Well, if I subtract 9 from both sides, I get x is equal to 15 again. I get the exact same solution as before. This is another technique that we can use when going and attempting to solve equations that have fraction values, or I should say rational expressions. So let's write down a procedure for what we did here. In this method, the goal is to clear all of the denominators. So what did we do first? We first identified a common denominator. Once we had that common denominator, we said to multiply it to both sides of the equation. When you multiplied it to both sides, we want to simplify what we end up with. And I'm going to put a little note here. All denominators, I was going to say should, all denominators must go away. Or maybe I will say all denominators must become a 1, okay? So all the denominators are just going to cancel out. They're going to divide out and become a 1, all right? So we are just dealing with whole numbers. Once you have all of that simplified, go ahead and solve like normal. And then the last step I'll say here is to check your answer. Make sure you have the correct solution. So here are two methods for going about and solving these rational equations. One method relies on combining all of the fractions together into one thing on one side and one fraction on the other side, and then using cross-multiplying to get rid of the two fractions. The other technique using the clearing method, gets rid of all the fractions first, and then combines everything together. You choose which technique you like. For me personally, I like method 2. I like to clear fractions. That's just me. A lot of other people really like the work that they've done when it comes to combining rational expressions together and simplifying them. So they're all about method 1. That's fine. Both will work. Just make sure you have a technique that you're confident with using. What I'd like us to do right now is to try a couple practice problems out. What I'd like you to do first is pause the video and try to solve this equation using whichever method you prefer, whichever is your preferred technique. Then what I'd like you to do is try to solve it again, this time with the alternative method, the method you're not the strongest with or it's not your particular go-to. I'm going to solve it in both ways. I'm going to first do this with method 1, then I'll go back and do it with method 2, the clearing fractions. So try it on your own with both techniques first, and then check your answer and your work with the techniques I've used. Hopefully you had some time to work through both techniques, and hopefully both techniques are making sense to you. If you have any questions about one or the other, if you're not feeling really strong in one of them, please let me know. I'm happy to help out. I'm going to first start by highlighting method number 1. That's where our attempt is to combine all of the fractions on one side into one fraction and making sure that we have one fraction on the other side. So to do this, I first need to have common denominators. Well, looking at the denominators here, I saw w plus 1 and w plus 1 again, and this denominator was just a 1. So I decided let's go ahead and let's try to get the 3, or the 3 over 1, to have a w plus 1 denominator. Well, whatever I do to the bottom, I also have to do to the top. So let's go ahead and multiply this through. We get 3w plus 3 over w plus 1 minus 6w over w plus 1 equaling 6 over w plus 1. We can now go ahead and combine the fractions together. Since we're subtracting, we're going to take 3w minus 6w, and that should just be a negative 3w, I believe. And we still have the plus 3 over w plus 1, equaling 6 over w plus 1. Now, we can go ahead and cross multiply, but it essentially really doesn't matter too much to us, because when I multiply both sides by w plus 1, that cancels out, and that cancels out. So really, all that I have to work with is the numerators. Negative 3w plus 3 equals 6. So I can subtract 3 from both sides. I get negative 3w equals 3, so w equals negative 1. Hopefully this technique is making sense to you. It essentially just relies on the idea that we are trying to combine two of the fractions together and make one fraction on one side, one fraction on the other side. Now I'm going to go back and I'm going to resolve this problem using method 2, the clearing fraction technique. This method just is method 1 in reverse. Instead of combining everything together and then getting rid of the fractions, we're going to get rid of all of the fractions first, and then we're going to combine everything. So let's take 3 minus 6w over w plus 1, and then we also have 6 over w plus 1 again. And what I want to do is I want to multiply both sides of the equation, because what you got to do to one side, you have to do to the other side. So I'm going to multiply both sides by a common denominator. Again, the denominators are a 1, a w plus 1, and another w plus 1. So what do they have in common? W plus 1. That is the common denominator. So I'm going to go ahead and distribute this through, and let's see what we get. As you can see, I've distributed the w plus 1 through to each of the terms, and I've left this just being a multiplication on the side. What I'd like to do right now is to actually go ahead and multiply these things and see what simplifies. Well, w plus 1 times 3, I just have to distribute the 3 through, to get 3w plus 3. Then, for w plus 1 times 6w over w plus 1, these are just going to cancel out, the w plus 1s, because they're one on top and one on the bottom. That just divides to be a 1. So we're left with a minus 6w, and the w plus 1 again is going to cancel out with the w plus 1 to leave us with 6. Hopefully you're recognizing that when I'm multiplying, I have one thing on the top and one thing on the bottom. They just cancel out, because if you have the same thing on the top and the bottom, that's just a 1. So that's why they're canceling out. We have the like terms of 3w and negative 6w to be negative 3w plus 3 equaling 6. If I subtract 3 from both sides, I get negative 3w equals 3, so w equals negative 1. Again, we get the same solution as before. So hopefully you're seeing how this clearing fractions techniques worked. We did this before when we would work with fractions that have numbers in the denominators. Now it's the exact same idea, except now we have polynomials in the denominators, and that's affecting what our common multiple we're multiplying both sides by is. Now, the last step in each of these problems was to check our work. So I should go back and I should probably do that. In both problems, we got a negative 1. So I'm going to take this negative 1 and I'm going to plug it back into the original equation. None of these simplified versions. I'm just going to go right back to where we started and I'm going to see if this works. So I'm subbing a negative 1 in for w and we end up with 3. The double negatives make a positive. 6 over... Oh, that's a 0. Negative 1 plus 1 is just a 0. And then I have 6 over negative 1 plus 1 is 0 again. So this is a problem for us. This actually doesn't work. This is an issue. I'm getting an error because these are not allowed. And so I just solved this equation for a value for the variable, and what I got actually doesn't work. What's the issue with this? Well, the problem that we have here is when we're attempting to solve with rational equations, we can run into extraneous solutions. Extraneous solutions are values that we get, things that we can achieve or we can solve a variable for when normally solving an equation, but when we plug them back in, they don't work. The trouble here is when we went and we were solving this, we attempted to solve it like we would solve a linear equation. This problem, this rational, has a domain that's not complete. Linear equations have domains of negative infinity to infinity. These have domains that aren't complete. They have asymptotes, things that can't be plugged in for the variable. So that's partially why we're going to have the risk of sometimes our solutions that are being produced are going to be extraneous, meaning they're really not going to be solutions because they're not going to work. This is why it's incredibly important to check your work. You need to see, does your answer actually solve the problem, or does the problem have one of these extraneous solutions? Let's do one more problem. In this problem, I'd like you to pause the video before we get to the solution, and I'd like you to try solving these both ways, okay? Remind yourself of what the goals are for each of the methods and attempt to solve the problem for the variable b. When you go about working with this equation, notice that the denominators can still be factored down. That's going to be important because if we're trying to determine a common denominator, we need to know what the factors are. So definitely, first thing you should do is go and factor down any of the polynomials. Try to factor down, in particular, any of the denominators. What I'm now going to do is method 1, where my goal is to combine these fractions into one fraction. To do this, I'm going to try to get them to have a common denominator. Well, this denominator had b plus 2, but it didn't have a b minus 2. And this denominator had a b minus 2, but it didn't have a b plus 2. So I'm going to multiply them by each other. So let's multiply the first one by b minus 2 over b minus 2. Then we're going to add on 2 over b minus 2, and we're going to multiply this one by the other denominator of b plus 2. Notice that these denominators are the same as these, so I don't need to change anything. And we will have this equal to b plus 2, b minus 2, all underneath 8. Let's go ahead and multiply these fractions together, these rational expressions. We're going to distribute it through to get 4b minus 8 over b plus 2 times b minus 2. And I'm going to add a 2b plus 4 over b plus 2 times b minus 2. And that's going to equal the b plus 2, b minus 2, all underneath 8. So let's go ahead and add these fractions together. We can add the numerators to get 4b plus 2b is 6b. Negative 8 and positive 4 is negative 4. And that's all over b plus 2, b minus 2. And we'll set that equal to 8 over the same thing. Now, we could cross multiply, but really, again, when we just multiply both sides by the same value, they're just going to cancel out. So we can just work with the numerator, 6b minus 4 equaling 8. I could add 4 to both sides, and we get 6b equaling 12. Dividing by 6, we get b equals 2 as our final solution using this method 1, using this technique where we try to combine all the fractions together. What I'd like to do now is take another moment and solve this using the clearing fractions technique. I want to make sure that we can all see how both methods are solved and how both methods might be used in certain practice problems. So I'm going to take the 4 over b plus 2 plus 2 over b minus 2, and then I have the 8 all over b squared minus 4. And what my goal here is going to be is to multiply both of these by the same value. So the common denominator we said before was b plus 2 times b minus 2. And what we do to one side, we have to do to the other. So let's see, we have b plus 2 times b minus 2 times 4 over b plus 2. All right, then I have to multiply the b plus 2 times b minus 2 by 2 over b minus 2. Oh boy, this is a lot. And notice here that the b plus 2 and the b minus 2 cancel out with this denominator. So all we have left is the 8. So after some time, we can see what quantities will cancel, and we're left with what we can actually work with. As we can see, of all the terms that go through and actually simplify, all of the denominators have canceled out. They've all simplified to just a 1 value. So now we can combine our like terms. We have a 4b and a 2b that makes a 6b. Negative 8 and 4 is negative 4. That's equal to 8. If I add 4 to both sides, I get 12. B is equal to 2. Again, this is the technique where I'm using the clearing fractions method. What I've done is I've found the common denominator and I've multiplied it through. so that way we get rid of all of the other denominators. Hopefully these problems are making sense, and hopefully these two methods are making sense to you as well. If you have any questions about them or want any updates, feel free to let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Until next time, take care.